Okay, so today we're going to talk about hashing, which is most important thing in the computer science and then in the algorithm. And let's solve this problem today. Problem today is your task is to do read n numbers and printing them in sorted order by using only minimum, successor, insert, and search. And I want that complexity of the n log n. Okay. Okay, let's solve this. So what you can do, so I can use minimum. I can use minimum. I can use successor. I can use insert. I can use search. And my job is read n numbers, print them in order. Okay, who want to try?
Can I go? This
Professor?
is Jung-hoon.
Yep.
When you say insert, does it insert it like at the back of the at the end of the tree?
Oh? What?
When you say insert, does it insert it just at the back of the dictionary, or it inserts it into the proper order?
We are implementing dictionary concept with using a balanced tree. So if you don't get the point, I will gonna solve it with the Jung-hoon, then you'll get the point. Okay, Jung-hoon, can you try?
Yes. First, start with the minimum. Find the minimum and print it out, and then find the successor of the minimum and print it out, and from then repeating find successor and print, successor and print, repeat that operation n times. Then we are repeating log n time operation in n times, so it is n log n.
Okay, good point. Anyone else?
I think before, my name is Youngjae, and before you start finding the minimum, you have to insert all elements in the balanced binary tree.
Okay, good point. Anyone
and
else?
Then do inner or traversal.
Okay, great. Anyone else? Okay, let me solve the first question. So my job is read n numbers, print them in order. Where should I start it? So for I equal 1 to n, insert I to true. Let's say is binary search tree. Then insert. What I did, insert. And the 4. From there, for I equal to n, find minimum, then print the minimum, and go to successor, then let's say find successor, then n. For to n, find the so I'm wrong in here. There's it should be find minimum for I to n print minimum, then find successor, then go to next, find the minimum, find the successor, find the minimum. You understand what I did? What's the complexity? For I equal to 1 to n, I did insertion, which is log n. Therefore, what I did is n log n. In here, find the minimum, which is log n. 1 to n print, this is 1 time. And I have to find the successor, which is n, which is log n. Therefore, in here, n, 1 plus log n. 1 plus log n is log n. Therefore, my complexity is n log n plus log n plus n log n, which is 2 times of n log n plus log n, which is log n. Clear? Too easy? Do you see how I solve it?
Yep.
Yep.
Okay. Everybody clear?
Professor, are we assuming that tree is initially empty?
Initially empty. So I have to put it in
okay.
that's why we need insert. Clear? Okay, so Youngjae, thank you. And Junghoon, thank you. And 1 second. Youngjae is Youngjae.
Professor?
Yeah.
Can you explain the log part again? When you add up the logs, I may have missed something.
Okay. Can I? Oh, it's more convenient. So here's my job. I have to read it. So you understand, right? My limitation is I only can do minimum, I only can do successor, and insert and search. What should I have to do? So for I equal 1 to n, I have to insert it. Insert to binary search tree or tree. Then end of this function. I just create a tree, binary search tree. Clear? Then what I have to do, I have to find minimum of tree. Then for I equal 1 to n, print minimum. Then find successor. Then update as minimum. Okay. So I just made one tree. Then from here, I just found the minimum of the tree. Then from 1 to n, print the minimum and find the successor. Let's see the complexity. This one is log n. Why is it log n? Because question says, your operation, search, insert, delete, minimum, maximum, successor, predecessor takes log n. Okay, this is given. Good?
Okay.
All right, go back to the point. Then this takes log n. So find the minimum, the tree, this takes log n. Okay, print the minimum, just 1 time, and find the successor is log n. But because we have a loop, therefore this portion is n log n. This portion is log n. This portion is n times 1 plus log n. And what's the total complexity? Which is n log n plus log n plus n 1 plus log n. Okay, which is 2 times of n log n plus log n. Because 1 plus log n is log n. And from here, this is only the constant, so we are ignoring it. And n log n plus log n is n log n. We can ignore the smaller part, right? Therefore, complexity is n log n. This is how you reasoning, and this is how you solve it. That is my intention. Everybody understand?
Professor, I have a question.
Yeah.
Why do you print minimum for n times?
This one?
Yeah.
Okay, so question says, your job is, your task is reading n numbers and printing them out in sorted order. That's the given task. Okay, so without printing, how do I know it is ordered or not? So I have to print it. Your program should print it, right? Clear? So your job, you
yeah.
want me to repeat? I can repeat.
I mean, the minimum will be always like one value, so that's what I'm confused.
Minimum is always, what do you mean?
Like, oh, maybe it's only me, but like,
Don't worry. I love your.
yeah, when you have n numbers, then they're really one minimum. So when you print n times minimums, they'll always print the same value.
Point. So what did I do? So if I make them a little clearer, do like eraser. So let's erase this point. Let's erase this point. Let me rewrite it. So let's say this is my value x is find minimum in true. In here, then print value x and value x is successor of
Oh, that's clear.
value x. Clear? Okay.
Yes,
so,
thank you.
Okay, so what we are doing here, we understand this. We made a one variable and find the minimum. Then from 1 to n, print the minimum. Then value x is keep updated as a successor of it. Then you are able to print in sorted order. Right? Everybody? Good? Not clear? Too easy?
Good.
Yep. Okay, so can I move on to next? Okay, so your job is, now you understand how I solved it, right? Let's practice. So your job is explain how you use a dictionary to sort n log n thing, the exact the same problem, but at this time you are only using minimum, insert, delete, and search. Now you are only doing insert in order traverse. Good. Do you understand the problem? So previously, I only able to use minimum, successor, insert, search. Now, I want you to do the same thing with the minimum, insert, delete, search, insert, in order, traverse. Two questions. Good. Everybody understand the problem?
Yes.
Okay, so you just watched how I solved it. Okay, how I solved it. And let's do this as a quiz. Okay, I'm gonna open the quiz. Write down on your note and upload your pictures. That will be nice.
Professor,
Yeah,
I have one question for the first one.
sure. Just
So, yeah,
10
sure.
seconds. Yeah.
Yep.
Yeah, quizzes 2-1. Ready? Okay, I just assigned the quiz 1. Then you can take a picture of it, what you did, and I think we can use as a to wake up your brain. Okay. All right. So comment. What was that?
For the first one, if assume that if I delete some node, do I assume that it's going to rebalance itself?
So delete meaning after deleting it, you have to maintain the answer to this, yes.
Okay.
After deleting, the binary search tree maintains this balance. Okay, so let's do this for 5 minutes, and we can share what we are thinking. So I'm gonna pause the recording here. Recording. All right. Yuha, you wanna try?
Yes.
Yeah.
So I'm doing number 1.
Yeah.
The top one. Okay.
Mm.
So I did it with for I1 to N. Then I1 to N, and then it's I equals 1 to N. And then I'm inserting into the BTS. BST. And then after the loop, I make a value X. And then find the minimum in the tree. And then I make another loop for I equals 1 to N. And then I print the value X. And then I delete the X from the BST. And then X is the minimum from the tree again. So change the X value from the new minimum from the tree. And then this is the end.
Okay, perfect. Everybody clear? Any comment on this? So how do you analyze it? So up to here to here, this guy is log n. This guy is log n. This is one time deleted, is log n. Value x is minimum, which is log n. Therefore, n log n, this is log n. It is n times 1 plus log n plus log n. Therefore, plus sum that all. So you n log n plus log n plus n times 1 plus 2 log n, which is n log n plus log n plus 2n times log n. Indeed, we can ignore this, then 3n log n, which is n log n. N log n. Okay, this is how you analyze your program. Good. All right. Thank you. Yuha. Okay. Next one is Pigeon. Can you do the third one?
Yeah, okay. So what I wanted to do was just find the minimum first and then delete it right after. So first I of course initialize the tree and then do a while loop after that makes it traverse from I to N, I guess, to the end. And then
from here you want to for loop I to N, then
yeah, and after that we would want to use the minimum function to find the minimum of the
third question. So let's want to do the second one.
Oh, you mean the second one?
Yeah, the insert and in order traverse. So the Yuha did a perfect answer for the first question. So let's solve the second one.
Oh, okay. So Okay, so first I initialize the tree, and then while it's not I to n.
So you want to use a
So
while.
yeah, go to the end, like I to n,
Oh,
and then
okay with the I
yeah,
to n.
read find the minimum, and then
So there is no minimum function in here. You can't use minimum.
oh wait,
In the second question, we only can use insert and in-order traverse. So PK, can you try?
The second one, you mean?
Yeah.
I didn't go that far.
Okay.
I
so
still trying to figure out the first one.
Sinjae Kang.
I'm not sure about this too. Sorry.
Okay. Hongmin. Hongmin, no. No answer. Who want to try?
I can go.
Yeah.
Okay, go ahead. Suin, it was your voice, right?
Yes, but somebody talked first, I guess.
Don't worry, you can first.
Okay, thank you.
Right.
So first of all, we can insert the old item into the tree.
Okay.
So I want to make a for loop for I equals 1 to n. Insert the old item into the BST.
Okay.
And then we just simply execute the in order traverse.
So the complexity. So BST is log n. This is n, therefore this part is n log n. So this one is log n, right? So you mean in order traverse inside of in order traverse, you are doing print, right? Okay, therefore the n log n plus log n is eventually n log n. Okay, thank you, Swin.
Thank you.
Okay, Yongho, you left the comment. Okay, I'm sorry, I missed it. All right, everybody clear about the second question?
Yes.
Okay, thank you. This is how you analyze it. Can I move on to the hashing?
Professor?
Yeah.
You said in order traverser, in order is log n or on?
You know, the traverse itself is log n because you know the traverse should be n log n. Sorry. So I thought the you know the traverse was inside of the sixth operation. So you know the traverse is given n log n. It usually yes. Therefore, it should be you know the traverse should be n log n. So 2 times of n log n. Therefore, it is n log n. Yeah. Thank you, Hassan.
I thought it was log. I mean, I thought it was I thought it was on, not n log n. Can you explain why it's n log n?
Oh, log n. So 1 time. So n time. Think about it. Okay, you know the traverse. So what I meant was in here is in order traverse as a log n, right? But if you ask what does it take in the in-order traverse? In-order traverse and actually takes a big O n time. You read through value, just one, and you are able to go to left, me, and right. Left, me, right. That only takes big O n. Did I clarify? So what I meant to initially, I meant to in-order traverse one of the functions, but I didn't clear out in here. So that's why I solved this question like this. So if n log n that I talk about is my mistake. But if you ask me what is the complexity of the in-order traverse is a big O n. Is it clear?
All right. Yeah. Thank you.
All right, thank you. It's a Hassan, right?
Yep.
Okay, thank you.
Professor, is quite trivial, but do we really need search function there? Like, we
The
can just
third,
find the minimum.
the second question and the first one and the second one, right?
I mean, the first one. Yeah,
yeah.
yeah.
One and this one.
Yeah.
Right. It's not necessary, but based on your imagination, you can use it.
Okay,
so I don't
I
use
see.
everything, then it is too obvious. I try to open more doors. That's what I said.
Okay.
All right. Clear? Okay. So hash table. So we're gonna talk about hash table today. So we understand what is hash table, and hash tables are a very practical way to maintain the dictionary. Oh, we know what the dictionary is. To do a dictionary, we do all 6 operations, right? The idea is simply that looking at the item and array just once and have an index. Because I have a key value, then go to the key value, I'm looking for my value. That's how the hash function works. Hash function is mathematical function which maps key to the integers. Okay, something like this. So if I have in here, I put it here, to there, go to there, go to there. But the main problem, the major problem with the hash function is collision. Okay, so let's solve this. Say I have record and Q, A, B, C, D, E, G, H, and let's say key is 4, 4, 4, 5, 4, 5, 4, 6. How does this hash function work? Let's say I'm saying let's say I'm using open address. We have a key from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's say A, 4. Okay, no problem. B, someone there. What do? I go to next possible. B there. C, someone there. I go to there. D, someone there. Next available. No. Next available. No. Next available. Okay. E, I go to there. Someone there. Next available. Next available. Next available. F, someone there. Next available. G, H, 8, someone there. Okay. This is how you do next the open address. What's an issue with this? Inserting is not that critical, but the problem is the main reason why we are doing hashing is to find the value quickly. Let's say I want to find H. Then using my hash function, then it turns out my hash function says 8. Then I go to that H. This is not 8. Go next. Not 8. Not H. Not H. And I just found it. How long does it take? Longer than a one time, right? In the worst case, something like F. Let's say I'm looking for F. Then after hash function, it turns out my hash key is 4. Then I go to my hash key. Someone there, but it's not F. Then what do? Go to next. Go to next. I just found it. It takes a while to find it. This is not efficient. Then how can you solve this? There's many mechanisms to solve it. The second one is chaining. So same question with the chaining. So A, B, C, D, E, F, G, H, and 4, 4, 5, 4, 5, 4, 6. So chaining is basically a linked list. 1, 2, 3, 4, 5, 6, 7, 8, 9. So everything initially is set to no, 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 no. A up, since it is no, hey, I can put it A in here, then I can set no in here. Okay, then let's solve this one. B, oh, same function is not empty. Therefore, what do? I have two mechanisms. I may append in the end, or I may append in here. Which one is a better option, 1 or 2? Let's think about why. So do you understand what I'm doing? So hash function just collided in the chaining mechanism. I have two options. Add append B at the tail of the existing, or append B at the head of the existing. What is better and why you think in that way? Okay, let's think about for 1 minute, and I'm gonna pick Taeyong, Jungmin, and Andrea, and Yongho. Okay, sequentially. So let's say the Yongho first, because he sent the message he want to do this. Okay. So after Yongho, Taeyong, Jungmin, Adrian.
Professor, can you repeat the question, please?
Okay. So you understand the open addressing, right? I put it the value. If there is a collide, I'm just finding next available, which is not efficient. Why? When I'm looking for this value, it takes a while. It is very inefficient, right? So I want to solve it by using a linked list. Then with this technique called the chaining, say I want to put it that A is to solve because it is null point. But B, I try to put it. So which way should I do it? Option 1, I'm just appending at the end of the existing, or I'm going to append at the head of the existing. Which one is better, and why are you thinking that way? That's my question. Clear? You may append your B in here, or you may append B in at the head of it. Which one is more efficient? Let's think about it. Just for 1 minute.
I think I will go for option 2.
Option 2 is better. Why?
If I choose option 1, then whenever I insert new element, then I have to iterate the previous elements to get the last value.
Okay, perfect. Perfect answer. Anyone else? Who like to do one option? Who like to choose the first option? Nobody? So everybody think a second one, the option 2 is a better? Okay. So
first option can be better.
Huh?
I think first can be good.
Why?
Because in order to link new element between A and 4, I have to cut the link between 4 and A, and link 4 and B, and link B and A. But if I put the end, I can just link B to A. So it takes less operation.
We try. Anyone else? This is Jung-hoon, right?
Yeah, right.
Okay, thank you. Anyone else? No? Okay, so actually 2 is more efficient. I'm going to explain why. Let's say I keep appending at the tail of it. what should I do? Then from here, go to next, keep looking for null. Then from here, null 2, I'm creating it. Then I make null. Then it will be D, 0, and F, something like this. Okay, keep maintaining. Then if I compare to different mechanism, if I do A, let's say it was a position 4, 2, A, then 0. Then if I'm adding B, what should I do? Create the B and direct to A, then null point, current point to B. Then if I reshuffle it, it look like B, A, and 0. Okay, then I'm going to face B, do the same thing. Then EF, then I have to do F, do the same thing. Okay. Then if you look at in here, I don't need to worry about all the tails in here. I only need to care about this. But if I choose the first one, then I have to care about all my head, the existing value, then one before null point to me. Okay, that all point, it could be very long, then I have to care about all long cases. Therefore, it is inefficient. So if in this case, the head of it, and only care about the head, only care about head, that's more efficient to insert to the this list. Then that is the advantage of the chaining. So let me erase this. So did I satisfy the explanation? So let's do this. So if I'm telling you in practice and practically, the adding to head is much more efficient. So let's say I had a right, then B, A, C, okay, null 2, C, and D is 4 again. Okay, solve it. E is 5. F is 4. Solve it. And G is a 6. And H was 8. H. Okay, this is how it look like. So what's the advantage of this? Let's say I'm looking for G, then I can instantly find it. In the worst case, let's say I'm looking for A. I'll go to 4, then I can search 4 times. If I'm looking for F, I'm go to there, I can find it in 1 time. Okay, much better than previous one. Okay, then let's do one little, this is still chaining. So we have to understand, let's say another example. My record is A, B, C, D, E, X, Y, G, and my key is 4, 8, 2, 11, 4, 11, 5, and 1. Okay. So that is linked list concept. Let's solve it in reality. Real memory state. So my H of K is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 is enough. Then initially it is all set to null. Okay, and let's do this. How does it look like? So my memory bank should look like information. It is all initially null. Okay, let's solve this problem. So what do I do? Let's say A is a 4. Oh, A, okay. Then I can put it 1 because my first memory is available is here and put my information. And the B is 8. B is 8. Then I do E. Okay. Then C is a 2. Put C. My information is D is 11. D is 11. D is 11. And this position 4. E is a 4. Oh, something there. And 5 is 2. Then my next is 1. Do you see what I did? So I just accessed until here is no issue. From here I start to causing problem, right? So go to there, then go to 1. Oh, that's not empty. So I put my information at the first available, then I link to the previous one. Then and keep doing this. It's 4 is 11, and which is X. 4 is X. X is 11, therefore, which is 6. And my information should be 4. And Y is a 5. Y is 5, no problem. Y is a 5. Y is 5. Position 7. Okay. Z is 1. Okay, G is 1. Good. Position 8. Okay. Do you see what I used? Okay, I just used the memory bank and using my hash function. It only maintains one value, one latest value. Then if I'm looking for D, D is a key 11, go to that, go to key 11, I go to the 6. Oh, that's not D, then go to 4. Oh, here it is. Okay, let's say I'm looking for Y, then my key is a 5. 5 says go to 7 position. Oh, here's Y. Okay, let's say, what's the worst case? Worst case is looking for E or X. Let's looking for E first. E, go to 4. My hash key says go to function 4, and it says go to 5. Oh, I just found it. If not, if I'm looking for A, my hash key says 4. Oh, I go to there, go to the function 5, I go to the position 5. Okay, this is not matching. It says I'll go to 1. Then go to 1. Oh, I just found it. Okay, do you see what I did? So actual linked list is not achievable in memory stack, but you can solve this in memory bank. Very simple. Okay, this is called the chaining. I hope this is not complex, right? Everybody clear how I did it?
Yes.
Okay, maybe it's too simple for you guys. If you have a question, please. So go back to the slide. So collision happened. So what should I do? Just what I did was open addressing something like, which is available, go to next, but it is inefficient. Then we are doing chaining. Chaining something like this, and we can implement it in the memory stack, okay, memory bank. So chaining is easy, but devotes a considerable amount of memory to pointer, which could be used to make a table larger. So this case, we make table larger, but we have ability to solve it by chaining in memory. Clear? Everybody clear? So chaining is easy, but devotes a considerable amount of memory because I have to maintain the all linked list. You know what? I can do a simpler way. Okay. This is how actually we use it today in the industry. Okay, go back to the point. So hash function, we know what it is. Okay, we hash it somehow. How do you hash it? We usually use like a big number to the smaller numbers. So data into smaller key features. Okay, that key feature is usually a prime number. Okay, not too close to the whole value, but the smaller values. Okay, so bad hash function. What is bad hash function? For example, let's say you may have national identification number. The first 2 digits says the year you born. If I do hash function based on the year you born, that is hash function. You are usually between 97 or 98, right? Then your all buckets are put in here. That is poor hash function. But what if I use the last 2 of it? Everybody is like random. Therefore, I can distribute it, your values evenly around. That is good hash function. So how do you pick the good hash function? Make your prime number correctly. Okay. So performance. So you have to have, we have to have a good prime number to use the hash function. That's why we're using prime number. Okay. All right. So performance of set operation. Say remember the hash function in your head. What's the search take in the good hash function? It takes 1 time. My expect sentence 1 time. Just go to that. Oh, there's value. I found it. What's the worst case? Worst case is your values are chaining all the values in a 1 hash function. How long does it take? And time. Clear? Same thing. Insertion, I'm expecting 1 time. Oh, empty function, empty bucket, I can put it. Worst case, oh, everybody else was put it there, so I put it in their bucket. That takes n time. Delete. Oh, I want to delete that guy. If there's only 1 value, okay, I can delete it easily on expectation. But the worst case, oh, right, I have to maintain all this chaining. That's the worst case. Okay. So mean, max, predecessor, and successor, and big O n plus m expected and worst case. What is it? So let's say this hash function. And I want to find this guy's next. In the view of the hash function. Hash function is, it don't do any sorting, but it is only inserting just head of it. So I don't do the sorting inside the bucket. Worst case, I have to care about all these members and all this members. Let's say it is distributed in here. How can I find the next of it? I don't know. I have to read through everybody, which is n plus m. All the numbers and all the buckets. You have to run through all the buckets and all the numbers. Therefore, is n plus n. Clear? And the mean and max, I don't know which one is mean, which one is max. I have to read through everybody. Okay, that's this way. So programmatically, hash function is open best data structure for maintain a dictionary. The worst case is unpredictable. So the best worst case bound come from balanced binary tree. So if you maintain the balanced binary tree, that is okay. Okay, but if your tree is unbalanced like this one, skewed in one bucket, it takes a while. So if I have one nice, if I maintain the balanced tree, I can expect reasonable cost. Therefore, what's the best case to do that? Best practice to do that is to find your hash function in a smart way. Okay, usually we're using prime number. Okay, so hashing. What does this mean? So Woody Member is the CTO of the Google, and he's the co-founder of the Google, and says that three most important thing in the Google is hashing, and hashing. So hashing has a variety of the clever application beyond just speeding up search. It's giving you short but distinctive representative of the larger document. Okay, so let's do one application. Application is the new document is different from the rest of the large corpus. How can you find your document is original out of the large data set? Any comment? Using hashing is the key. Anyone? Okay, I'm gonna pick Yu Jungmin. Any idea? Then I'm gonna pick Adrian and Roshan and Subin. I'm gonna pick you. Okay, so Jungmin, your comment on this?
I think.
Okay.
Can I continue or?
Okay, Jungmin, you don't want to?
Yes. Can you go first?
Okay, go ahead, Janar.
I think comparing like raw documents using hash is going to be complicated because documents can be very big. So first, those documents are stored as a hash function because they were pre-processed before. Maybe they were labeled by the words inside of it or things like that. So I think to compare a new document with the other, we have to pre-process it first, like make labels or like find the most occurring word, and then based on that, search other documents.
So, okay, so point.
A lot of words, a lot of keys.
Okay, anyone else? I got your point, thank you.
Can I try, Professor?
Sure. Go back.
Yeah. I think like maybe they are using two hashings, hashing inside hashing.
Hashing inside hashing, okay.
That way, like when you like, for example, distribute elements inside the hashing, and if some of them like has like maybe 100 elements, you can distribute them inside other hashing. That way to like, and I think it will be like faster.
Okay. Good point. So, do you know that all the PDFs? So, if you write the PDF, that your Adobe function generate the hash key. Okay. So let's say you upload your same file to your Google Docs. They notice that, oh, this is the same copy of it. Okay, you want to replace it or no? that the file name is one check. If the file name is the same, then also there is originality check. Meaning if every PDF their own hash function that is given by Adobe. Okay, so any comment is updated. Then they are creating new version, recognized as a new version, revised version. And this is being used in Git and SVN using this mechanism. Do you use the SVN and Git? I'm sure you use the Git, but SVN is the old version of the Git. It's more simple. So what they do is whatever you're typing in here, if the hash key is changed, meaning they recognize your updated version, recognize as updated version. Okay, so since I have to finish this, and let me go to a little faster. So as part of this question of plagiarism from a part of the document in a large corpus, how can I check it? So hash overlapping window meaning, so let's say your original document, let's say Yuha did one document, and there's a bad guy. This bad guy just copy from her and send a 2 copy of it. But bad guy 3 is a clever. They copy from some section of it and they make their own solution. This case, I can detect, not an issue, right? With the hash function. But this guy, how can I find this guy? So if I do section by section or line by line, hash key, oh, that hash key is consecutively overlapped. Then we have plagiarism detector. So Blackboard support the plagiarism program, and there's many programs which can detect the plagiarism. Okay, that is what they do. Line by line, they make a hash key, and if this pattern appears, there is something. Can you check this? Right, every time you submitted the conference paper, journal paper, they are checking it too. Okay, so this is how we're working. Go back to the next. So how can I convince you that the file isn't changed? Okay, like some auction system. Everybody bidding. Okay, then close the auction. Then auctioneer open the packet. Okay, you have to pay, you are the pick, and you will pay it. Okay, how do you make sure this file is not contaminated? Okay, compare this value and this value, is it correct? Then, okay, you are the authenticate. Then I trust you. Okay, in an auction, in real auction, we are using this hash. In an online auction, we are using this function. So online vote, keep maintaining the hash key. If the hash key is contaminated, I think something is edited, which is invalidate the value. Okay. So let's find the substring pattern matching. Substring pattern matching, let's say a text string T, a pattern P. Okay, so let's say my text is a Bible, my pattern is my name, my first name. So does T contain the pattern P as a substring? If so, where? We are always doing in PDF search function, and by doing this, I can find it quickly. Then how can you find so quickly in a PDF version and so quickly in the Windows doc? How can they find so quickly? Then how is Google working? How can they find in a 0.000 second so quickly? Because all the data you submitted is hashed by the Google. That's the power of Google. And all the functions are fast enough in order. So how the Jihoon, my first name is sorted, the hash. Start with the J, hash J is one key, and the JI is the second key, JIH, third key, JIHOO is fifth key. And if this doesn't make any sense, it's not part of the dictionary or it's not part of the name, then ignore. Oh, I can take it. Then that is recommendation mechanism. If I type J, then they'll say JI, JIHO, JIHON. They don't show this because it is all hashed. Okay, that is how the auto spelling recommendation, something like it. Yeah. Okay, so how they do it? Basically, brute force. The simplest algorithm to search the presence of the pattern string P is you keep comparing. So you have to read through everybody in text and everybody in your pattern. It takes too long. So what is a better mechanism to do this? So since we are running out of time, the basic thing is using hash. So my word is hashed. Something like this. Let's say you have all the Bibles has a text, all the text. Not by the word, but also the fraction of the word is also hashed. Then I can find, let's say, someone who sleeps. I have ability to find the sleep, but at the same time, I can always, SLE is also findable, also searchable. Not only by word, but the fraction of the word, which makes sense. Okay, therefore we can find the context very quickly. Okay, from SN. Okay. So this is how the hash function works. And the back of the Google is complete hash. And back of the good search engine is completely hash. Okay, so we covered the hash function. Any question? No?
Will this be inclusive in the midterm?
Yeah, until this point, hash function.
Professor?
Yeah.
Can you tell us what kind of questions will you give us in the test?
So I didn't make an exam yet. So it is doable if you understand all the slides. But it will be never same from previous, it will be never same from existing problem. So my recommendation is read the book, read the slide. If you understand the topic that I am talking, then it will be fine. The usual student, based on my previous experience, they'll get the 80 to 90% score.
Okay, thank you.
All right. Anything else? All right. Next Monday is our first midterm, and good luck on it. And I will upload my video and my slide after this talk. Okay. All right. Thank you, guys.
Thank you.
Thank you.
Thank you.